Uniform circular motion. When we talked previously about uniform linear motion, we said that it was motion at a constant velocity. Motion at a constant velocity means motion in a straight line at a constant speed. Uniform circular motion is similar in that it is motion in a circle at a constant speed. Remember, velocity is a vector quantity with magnitude and direction. Since it's circular motion, the direction of motion is constantly changing, which means that velocity is not constant. But the speed, which is the magnitude of the velocity, does stay constant. In uniform circular motion, the time it takes to complete one circle is called the period, capital T, of the motion. What is the period of a second hand on a stopwatch? How long does it take to go around in one circle? It takes a second hand 60 seconds to go around the stopwatch one time. Let's look at uniform circular motion with our stopwatch a little more. Our stopwatch is started and runs for 1 minute. The length of the second hand is 1.8 centimeters. What are A, the speed of the second hand, B, the velocity of the second hand after 15 seconds, C, the velocity of the second hand after 30 seconds, and D, the average acceleration of the second hand between 15 and 30 seconds. Let's start with part A. What are we given? The length of our second hand, which we will call R, is 1.8 centimeters. Let's go ahead and convert this to our SI unit of meters. We get 1.8 times 10 to the minus 2 meters. We're also told that the stopwatch runs for 1 minute. That's a time of 60 seconds, which is also the period of our second hand. So we'll call that time capital T. Now, what are we looking for in part A? The speed of the second hand. Speed is the same thing as the magnitude of the velocity. Now we need an equation. We know that speed is equal to distance divided by time. What is the distance traveled by our second hand? It runs for 1 minute, making a full circle around the stopwatch. The distance around this circle can be given by its circumference, which is 2 times pi times the radius, which in this case is r. We can substitute this expression for distance into our speed expression to get 2 pi r over t, our time in this case. Next, we plug in our values for r and t. And now we can use our calculator to solve, getting an answer of 1.9 times 10 to the minus 3 meters per second for the speed of our second hand. For part B, we're given the same length of the second hand, but our time we're looking at is t equals 15 seconds. This time we're looking for the velocity, which includes both magnitude and direction. The magnitude of the velocity is the speed. We already found the speed in part A, and speed is constant since this is uniform circular motion. So it's the direction of the velocity at 15 seconds that we still need to find. The second hand is moving clockwise. At 15 seconds, what is the direction of the velocity of the second hand? The velocity is directed downward at 15 seconds because that's the direction that the second hand is moving at that time. So our answer for part B is 1.9 times 10 to the minus 3 meters per second downward. For part C, we're looking for the same thing, but at a time of 30 seconds. Again, the speed we found before is constant throughout the motion of the second hand, and it's the direction we're looking for. So at 30 seconds, what is the direction of the second hand's velocity? It's to the left. So our answer for part C is 1.9 times 10 to the minus 3 meters per second to the left. And lastly, we have part D. For part D, we're looking for the average acceleration of the second hand between 15 and 30 seconds. In part B, we found that the velocity at 15 seconds is 1.9 times 10 to the minus 3 meters per second down, And in part C, we found that the velocity at 30 seconds is 1.9 times 10 to the minus 3 meters per second to the left. And our change in time is 30 seconds minus 15 seconds, which is 15 seconds. Now we need an equation for average acceleration. This is delta v over delta t. How do we find delta v? Delta v in this case is v30 minus v15. So we substitute that into our expression for average acceleration. To find v30 minus v15, we have to do vector subtraction. First, we need our vector for v30, 1.9 times 10 to the minus 3 meters per second to the left. Next, we need our vector for v15, 1.9 times 10 to the minus 3 meters per second down. Since we're subtracting this vector from the first, we flip its direction, making it negative, and put it on the arrow end of our first vector. Our resultant vector, delta v, is this vector, v30 minus v15. We can now use the Pythagorean theorem to find the magnitude of this vector. Now we substitute this expression into our expression for the magnitude of the average acceleration, and we can plug in our known values for v15, v30, and delta t, and solve, getting an answer of 1.8 times 10 to the minus 4 meters per second squared for the magnitude of the average acceleration of the second hand between 15 and 30 seconds. This is only the magnitude though, and we also need the direction of the acceleration to find the complete vector. We'll define the direction of the average acceleration using this angle, theta. Remember, the direction of the average acceleration vector is the same direction as the direction of the delta v vector. We know from trigonometry that the tangent of this angle theta is equal to the magnitude of v15 divided by the magnitude of v30. Now we can solve this expression for theta. Since the magnitude of v15 and the magnitude of v30 are equal, we end up with theta being equal to the inverse tangent of 1. This gives us a value of theta equals 45 degrees above the left direction. So our combined final answer for the average acceleration of the second hand between 15 and 30 seconds is 1.8 times 10 to the minus 4 meters per second squared, 45 degrees above left. You can see that problems involving uniform circular motion use many of the concepts that we deal with in uniform linear motion, including making sure that your vectors have both magnitude and direction.